Okay, so let me just quickly go through this. Let me see what else I want to. Okay, yeah. So the lab which Shantanu was talking about, that's so I just created a lab for it and I put it here. So it's the same thing which he explained, very nicely. So just to kind of give you an overall idea why we are doing this is just like Shantanu was saying, there are many fields in VLSI. Not only that, when you're doing this, you kind of use it as a designer as well. So we already have a model. So maybe just quickly tell you the modeling process. So although you see the model parameters are coming from physics, right? Cox is epsilon Knox by Tox, aluminum sheet row is row of aluminum divided by the thickness and all that. But the thing is that the process is a lot more complicated. There are impurities, there are imperfections, and all that, and the models are not perfect and all that. So actually, till BSIM 4, like till BSIM 3, so level 1 and all that, these models were created purely empirically. So empirically in the sense, when a foundry came up with a new technology, let's say this is Nmos, which we're going to use, they will fabricate a bunch of test devices, and they'll get the test devices, and they'll do all these measurements actually physically on a characterization tool, and they'll measure this, and they'll extract all these parameters, and some of the parameters they will extract indirectly, like the doping, although they are, so let's say they're trying to do the doping 10 to the power 14 uh, per centimeter cube. That's what their intention. But when after the doping is done, it's something else because of all the imperfections in their tools and all that. So that's why they have to extract even that doping through measurements by doing sheet rows and stuff like that. Like you would have seen yesterday, we calculated the sheet row of aluminum, but then when we went to the document which uses aluminum, the sheet row is different. And those differences are what you use the measurement to do it. So we are trying to give you that whole process, and plus sort of give you an insight into those models, like what is happening inside the model. So obviously we don't have access to the fab and vapor probe and all that, but we have an access to a very good model. So the model we are going to use, the 0.5 micron technology, the scaling, we have a level 49 BCM 3V1 model. Okay. So, and if you go to, um, so that model is read only now, but you can copy it to your directory if you want to take a look at it. So if you go to, for example, once you have your lab instance, you go to project, EDA, technology, um, technology, SCN4M, this is the one we're going to use. And then you go to the live directory models. So you see here there are three directories here, FF, NOM, and SS. They basically stand for three corners. So NOM is typically what typical values what you would get out from the lab. Like we were saying, the mu n you're calculating, that will actually vary. And the variation is from process to process. The LD which you're putting in the model, the junction leakage into the gate, that also will vary from process to process. When I say process to process, every time a wafer comes out, it's going to be within those bounds limits. It's not going to be exact. So that's why they give you different models to make sure that you can design and make sure your spec meets for all the corners, all the limits. So let's go to the nominal corner. And if you go into the nominal corner, so there is a model for Nmos and there's a model for Pmos. So let's look at the Nmos model. So you can see this is a BSIM model, and it should say somewhere, yeah, so it says level 49. And like Santanu was explaining in the morning, level 49 is BSIM 3, and it says a version. So you can see the version also, it says it's 3V1. Okay, and you can see that you used only 5 parameters, but you can see that there are, I mean, how many parameters are here? So 39 minus 8, 31 times 3, almost 90 plus parameters, right? And they're much more complicated now. So all these parameters are mostly measured parameters. Pretty much all of them are measured parameters. Okay, so that's the exercise we are trying to do here. So what we're trying to do is that we are going to give you this model, right? So obviously you have this model, and this is a very accurate model, which is very close to what you're going to get if you fabricate it in this technology. Okay, and then what you're going to do is you're going to pretend that as if this is your chip which you got back and you don't have a model. And in Spice, you're going to do all these simulations, right? So you do the simulation, extract VT, mu and Cox, um, and um, gamma, the body effect, the lambda from this, and so on. And then you create a level 1 model, right? Using um, the, the format which Shantanu showed you. You create that, and then what you do is you simulate with level 1 and you simulate with level 49 and overlap them. So you do a IV characteristics for both models, and I've just given you the problem to do only Nmos, so you can do the Pmos as well, and you overlap them, and that will give you an idea like what are the differences in the model, how off it can be. But at the same time, for a user who's designing it, it's still good. Even if it is off by 20%, it gives you a direction on which you want to go. But 20%, if it is off in reality, that's a lot. But for a designer, 10-20% even is nothing. You can still get the design to as close as possible, then simulate it and figure it out. Okay. Uh, so that's so basically the first part of this lab is doing the extraction, like what Santanu was saying, and then the second part is you create the level 1 model, and I've said do two different widths and lengths and kind of show the difference over here. Okay, and so that's the first lab. So this lab will sort of get you started on the tool. So it'll force you to learn the tool as well and get you comfortable with models and doing the Nmos simulations. I mean the MOS simulations and so on. So this will be a great lab to, I think, start. And then after you have this, then we'll keep moving with the rest of our labs. Any questions on the lab? And you have to do the labs. Without the labs, this course is you might as well not do this course, right? These courses are, I mean, engineering courses are. So that's the reason why you get out of 4-year degree and then suddenly you don't know if a capacitor is linear element or non-linear element. That's because you just need to get your hands dirty. The assignment will do tomorrow in the lab session. Yes. But like as I said, by about 8 or 9, you should get your instances ready. Once you get that email, follow the instructions how to get it started. Once you do that, you're all set to go. So if you're feeling adventurous, the assignment is already posted. All the models and everything are there, and if you're familiar with Spice, just get going. Don't have to wait for tomorrow. But yeah, tomorrow we'll start. I mean, tomorrow we'll see. I think we might just do a real quick session on just simple Linux stuff, and then we'll get started. Okay, and also something will put an assignment for the problem assignments from yesterday, the MOS threshold and IV characteristics, and that will put an end date for like Monday evening or something, so that way you have enough time and you can use the weekends to do the labs as well. Okay, so question. So can we use the tools separately, like in separately downloading the tools, or they're interlinked with each other? The tools are already downloaded for you. You don't have to download anything. So maybe I didn't understand your question. Can you come online and explain? So Shakti, what do you mean by the tools separately? Oh, you should be able to
So,
unmute
sir,
it.
before we are using the Sui 2 app, so there we can use. I have downloaded it, the software. There we
Okay,
can use that.
right. Okay, here is the thing, right? The whole reason I do this is because, we're not system administrators here, right? We're forced to do system administration. This is something we do it for your good. And this is why we did the cloud, because the moment we give other people too, then we become system administrators. So we are getting this question, sir, this is not working, this is not working, that is not working, blah, blah, right? Yes,
Okay, sir.
you're free to do it. I mean, if you're comfortable with it and you want to do it, you do it. But
Okay, sir.
we will not support, an ounce of it, right? You can't come and
Yes.
say, oh, this ngSpice is not working. I have no idea what system you have. I have no time to go through it. Neither Samsung does. So that's the whole idea, is that now I have set it up that it's a homogeneous thing. If somebody is having a problem, everybody is having that same problem. I fix it. All 60 people's problems are fixed. Whereas with your method, I have to fix 60 individual problems for every problem. So it's like a nuclear bomb of problems. So, so yeah, you are free to do this lab on your own set of tools, but you're on your own, right? So if you're comfortable with it, yeah, of course, go
Okay,
ahead
sir.
and do it.
Thank you, sir. Yes.
Um, okay, any other questions?
Sir,
Oh, okay.
is
By
there,
the way, so Shakti, the tools you have, is it on Windows or Linux?
Sir, in Windows.
Okay, no Windows, please. You
Okay,
got
sir.
to, you have to work on Linux. Okay.
Yes, sir. Okay,
Yeah.
sir.
So if you have it on a Linux desktop, it's fine. I'll allow you to do it. If it is on Windows, no, not for this lab. You want to do it after that, that's fine. The
Okay, sir.
reason is because I mean, Linux is also part of this. I mean, I want people to get hands-on on Linux as much as possible. That's the biggest complaint I get. People mostly don't hire from us is obviously they lack fundamentals, which they have. But the other big problem is just the ignorance of um, general the computer, like just knowing simple programming and Linux a little bit, because VLSI is all Linux, right? You're not going to touch Windows at all in your lifetime. I mean, doing Word and all that, but you're going to just remain in the Linux and Unix environment. And all the good colleges, for some reason, they get a lot of Linux experience, and our students don't, and they're just so they don't want to deal with this. They don't want to teach people Linux before, and it's not a huge deterrent for people. But uh, if there is a guy, they interview and you are head on, right? Like they have selected one guy from NIT Rourkela and they've selected from you, and he knows exactly the same amount of CMOS as you do, but he's a terrific Linux user. I mean, they're just going to close their eyes and take him. That's for sure, right? So you're basically just making yourself disadvantageous for a tool which you should learn, overnight. So, I mean, you can go deeper and deeper, but at least the basics of it you should. So, yeah. So if you have your stuff on a Linux, like especially on a Debian or Ubuntu, and you want to do it on your own, that's fine. But like I said, obviously we can't support it, and but if you have on Windows, then I'll say you have to do it on this platform, because it has to be on Linux. And that's what I'll encourage everyone. It's like, even if you guys are using on Windows, install VirtualBox, load some distribution of Linux, either Ubuntu or LXLE or any of those. I mean, there are like 3,000 distros. Use one of the popular ones, and use the tools there, and avoid using mouse as much as possible when you are inside it. You should be using this shell all the time, right? This Unix shell, the bash shell. This is what you should be using. Like, even if you're trying to browse a file, and obviously I see people just go to a file manager. They'll open a file manager, Like for example, if I created a folder here, uh, so obviously the new Linux, and they'll just open this and they'll start browsing and all that. Just avoid that. Okay, just use um, the shell as much as possible. Okay, any other question on the lab?
Sir, is there any option that we can save our work?
Great point. Thanks for reminding me. So what I want you guys to do, which all of you should do, is get a GitHub account, right? Like this, like we have our lab one. Get a GitHub account, okay? It's free. You can have as many public accounts, and the nice thing is after GitHub was taken over by Microsoft, they allow you like I think 5 private repositories. So if you feel some of the stuff you want to keep it to yourself, just open a private repository. But um, so what you do is you basically open a GitHub um, account, create a repo for yourself. Like, we created a repository like SI2103 CMOS VLSI. You can exactly create the same one or put some other name so that you can create it in your home directory. And then clone that here, right? Somewhere here or some other directory. Don't name the same name and clone it. It'll just overwrite the whole thing. So you have to be careful. So let's say you name your GitHub repository Swadesh, Swadesh CMOS or something like that. You clone it and you're going to get a directory here called Swadesh CMOS, right? Then start doing your lab there, right? I showed you that do the lab in this directory, make directory lab. Instead, do it in your GitHub folder, and then you just keep pushing all your stuff into the GitHub, right? So what I mean by pushing is, so I'll show you an example. Let me do this. So this is this SI 2021 is actually a GitHub repository, which is this repository here, right? So I'll make a small change in the Unix terminal and show you how it gets reflected on your GitHub account. So let's say make a small change somewhere here. So yeah, let's say on the title, I'll just make a small change. Um, or I'll add something here. You see the GitHub repositories for a summer internship course. I'll make this bold. Okay, I'll make this bold and then I'll push it to GitHub and you'll see it gets reflected. So let me make that small change here. So CD, okay, README. The README file is, um, oops. Just 1 second, guys. Okay, sorry, I'm back. So, okay, so you can see when you create a repository, it creates this file called readme.md, and you want to keep that name as it is. It's called a markdown format. It's a tagged format like HTML. And if I open the file, you can see this is how the file looks like. So these are tagged format in the sense like if I add a hash, it becomes a heading one. If I had 3 double hashes, it becomes course content. And you can just search the web like markdown reference cheat sheet. Yeah, do markdown cheat. Where did it go? Cheat sheet. Um, okay, so you can see these are your markdown languages for which it gets rendered, nicely like this way. So let me go back here. So like as I said, so I'm going to make this summer internship as bold. So bold is you enclose whatever you want to make bold with two asterisks and it'll become bold. And you can see Vim actually recognizes Markdown, so it actually does a little bit formatting for you. So once you do that, and if I do git status, it'll tell me that, oh, I have modified all these views. I don't care about these two, but I care most about this one. So what you have to do is you have to do a git commit, means you want to commit this change, put some comment saying that updated readme.md, and then um, oh, I have to set this up. Yeah, so you have to do this um, configuration. Let me do that. So you have to do, so maybe this is a good thing to show it to you. So you basically have to configure it. So you can do git config user.email, and let's say this is a one-time setup. Once you do it, you don't have to. And then git config. Okay, once you do this, I think this should work now. Okay, did it. And then, so you first commit it. So that's the process in Git. New file, you have to first do a Git add. Modified file, you first do a commit, and then you do what's called Git push. So it'll push it to the repository. Here you have to give your credentials. Let me give it wrong. Oh, basically it's saying that there are some changes which are done in the main, so it's not able to push it. So first what you have to do is you have to do a git pull to make sure all the changes are reflected in your local one. So if you made, and just saying that you need to merge it because it finds difference, and if you are sure about it, which I'm here, so it'll merge it. And now you can push your change back into GitHub. So you do silicon VLSI. Okay, so now it's pushing it to, so the changes is done now. Now if I go back to my repository and just refresh the, and you can see it became bold, right? So essentially what I'm saying is that when you this lab, what you do is you go now, create a GitHub page account, create a repository, new repository called summer intern lab or something like that. And then you pull that in here. So instead of lab, let's say it'll be your repo name, it'll be called summer intern lab or whatever. And you basically maintain everything here, and all the changes as you're doing it, you just keep pushing it to your GitHub. And then everything is on the cloud. And once you're done with the lab, when they delete this instance, you don't care. You already have everything in the lab. So next place, or wherever you go, or you go home and you want to do it, you do a git pull there and you start working there. Okay, so it gets backed up, and it's beautiful. I mean, you can't get better than that. And what I would encourage you all is create a repo, and whatever you're learning, you create a documentation like this, right? And then this remains with you forever, right? For us, even for us, like this, right? Every time I need to refer something, I just go back to this page. I have the videos, I have the links, I have the reading assignments, and everything is in one place. Just don't put anything proprietary or copyright informations here. If you do, then make that thing private. Okay. um, so GitHub allows you to now do, I think, 4 or 5 private repos or something like that. So I think that was a long answer to a short question. So this, but did that, but I actually wanted to cover it, so it's good you reminded me. Any other question?
Sir, is there any tool that we can use for like designing any CMOS model that like not like a regular one, like we want to customize it in our own way and
Customize
then
what?
test?
Customize what again? A CMOS model?
Yes, sir. Like we want to create another model, and
Okay.
also we want to check its current VI characteristics. So is there any tool there?
So, for example, you want to create a BSIM model, your own
Yeah,
BSIM
kind
model.
of. Yes,
Okay.
sir.
Yeah, yeah, there are a lot of tools, right? So, like as I said, I personally don't do it, but so Santanu, do you remember that tool name which Nitish was using in Savia? What was the free tool name? Do you remember that name?
I see cap.
Huh? ICCAP. Yeah, yeah. So ICCAP. So ICCAP is one tool I think people use. That's an open source tool. So there are a lot of proprietary tools. Silvaco actually makes that's the most industry popular tool for creating models. So just what you're doing in this lab exercise, that's why I'm saying you do this lab exercise, because tomorrow you see, this is the problem, right? We train people and we say like, look, we don't know where you're going to end up, but you just whatever you need to learn, just learn it, because once you know it, you know it. And so like for example, this is the exercise I've done with most every student who does the CMOS design. And there was a bunch of people who ended up in CMOS, the ST Micros modeling team, but they just never paid attention to it when they were taught, and they were like, oh, what do I do? And if they went through this, they would just grasp it like in 5 seconds, because once you do this exercises and go through it, you're not going to forget it, because the principles are very simple once you go through it and you grasp it. It's just that, wherever you go, you're going to use a different tool and all that. So yeah, we had a guy who went into ST Micro's team, and um, he was using ICCAP. So basically, the thing which you're doing manually, you're able to do manually, is because it's only 5 variables, and it's a level 1 model, right? And I just showed you for the level 49, it's 100 parameters. So if you start doing it manually, then it's a lot. I mean, it is prone to error and so on. So these tools, what they do is they take minimal amount of input from you. You still have to give them inputs, right? You have to tell them. So for example, what you're doing in the lab right now, you're giving them, you're doing the slope and all that. So I think I've never used ICCAP, but in ICCAP, so what you do is you give these slopes, you give some bare minimum stuff, and then from that, it calculates all the derivative parameters from it and creates the BSIM model or EKV model or IGBT models or whatever other models. There are plenty other models also people use for different devices and so on. So yeah, so there are tools to use it. So I'll say, yeah, try ICCAP, because when one of the guys in Survey he was doing, we were kind of mentoring him, and he did a presentation, and it looked good to me. So yeah, I would try. That's the first thing I would try, ICCAP, because most of the tools used in the industry, they're paid tools, and usually it's the Silvaco tools. So, but those are very expensive. Okay, did I answer your questions for this? I don't know.
Yes, sir.
Okay, any other questions on the modeling part or what Santanu covered? One thing I wanted to maybe emphasize. People were saying, um, this is part of the model where, like, for example, something was saying pass LD, but some were saying, oh, it's part of the model. Why are we passing it? Uh, I mean, you're sort of right. A lot of it is just, see, you have to imagine it this way. This is a C program, right? Spice is a C program. And that C program has a function, and that function is what is calculating, and all the arguments to that function is the parameter in the model or the one you're sending it through the instance line, like the M1 drain source, blah, blah, and all that, right? Now, like in a C program, a lot of those parameters have their own default values embedded in, but you can always override them when you're passing it through a function, right? So it's kind of same here, is that the models are parameters. If a parameter, like for example, which Santanu was giving for the LD, if the LD is part of your model, which typically is, then you don't need to pass it, and you don't need to account for it in your calculation either. Like for your AD, PD, and W and L, you don't need to account for it because that's only the drawn length. And if it is there in the model file, then it will calculate on its own. If it is not in the model file, you pass it. If it is not in the model file and you're not passing it, but you know it, then you calculate it like what Santanu was saying. You include it in the source drain areas. You got it. So, but typically you always have those parameters. Model parameters are in the model, right? Because they are not design parameters. Design parameters are source areas, drain areas, W, L are your design parameters. Everything else is process parameters. If it is a process parameter, it goes into the model, right? So that's how it is. But a lot of times, the processes are so complex that they'll have a base model and they're passing parameters to it based on the corner temperature and so on. So for example, most of the TSMC models you'll see, they're actually subcircuits. They're not models, they're subcircuit, and there is a model inside that. So they pass all these parameters and all that, but typically that's all embedded inside it. Okay, so that's one thing I just wanted to point out is that um, you know it's just because it's in the model file doesn't mean you can't pass it. I mean, it depends on the simulator, but most simulators will allow you to overwrite it. So the overriding is uh, you know the precedence is basically if you don't assign the numbers, then it falls back to the default number which I showed you in that BCM manual. And like as I said, most of those numbers are uh, impractical and bogus numbers. So, except for like, let's say lambda, where if it is 0, it will still give you, intelligent result. But most others, like VT is 1 volt, and you're doing a 0.18, then that's bogus, obviously. So if you don't have it, then it obviously falls back to the default. If you have it in the model, then and don't pass it in your instance, obviously it falls back to the model file. But if you have it in the model file and passing it through the instance, then it'll fall back to that. But different spice simulators allows you some model parameters to be passed, some not, but mostly they do. Okay, is that clear to everyone? All right,
Yes,
so
sir.
okay, good. um, Now, everyone clear about all the modeling part which Santanu covered? I think everyone said yes, but I just want to make sure everyone, I mean, and what we covered right now. I mean, obviously, this is just to show you how to get to the lab, but obviously, the spice part and all that, you just have to, learn. But, we have time and you have access. Now you have 24/7 access to a dedicated desktop. You don't have to share it with anyone, so you have no excuse to not learn this stuff. Okay, so everyone in sync so far? Just raise your hand or thumbs up saying that I'm all good, I don't have any questions. At least I know you guys are awake. Everyone just raise your hand, thumbs up or whatever. I mean, I have a feeling some of you are just doing it for the heck of it, but that's still better than, like, I don't know what's going on with the rest of the guys. Like, yeah, just raise your hand. If all of you are good, have no doubts at all, just keep your hands raised. I just want to see the people who haven't raised their hand. What's their issue? Now, obviously,
They're sleeping.
okay. All right. So ECB4, 17 ECB4, whoever you are, is there something you don't get or don't follow?
Sir, actually, I have to like I have to do all those on my sister's laptop, so it's not ready right. So after the class, I have to go through the recordings and do all the installations and required work. So
I guess you're you are not following. You don't have to do any installation. That's what we've been saying.
no, sir.
But
Actually, we don't have Ubuntu. I don't have
so
a
that's why I'm
Ubuntu.
saying. So I guess you didn't. Were you listening to me? Why do you need Ubuntu?
For the Linux purpose. You said now it will be more compatible to do that.
So I guess you just came halfway through. Were you listening to me all the time?
No, sir. I joined it half.
Okay, that's why. No, you don't need a Ubuntu system. Basically, what I'm saying is that to avoid you needing a system, we have given you access on the web. So you're going to get access on the web. And please rename yourself so that I know who I'm talking to. Um,
Sir, Suman, sir.
Okay. So Sumant, yeah. So the whole, and that's what I've been saying from the beginning is that the whole idea is I don't want you people to go through this. Like, oh, I don't have uh, a desktop which can do VirtualBox. I don't have a Ubuntu system. You know, this that. So we create, we are paying this company to create this web-based virtual desktop. So all you need is a web browser, Sumant. Okay. So you don't need anything else, just a web browser and you're ready, good to go. Internet connection, obviously, but then also you don't need um, any decent speed. So, uh, I mean, you just like even if you have just a hotspot with half a megabyte connection, that'll work fine with this one. It shouldn't be a problem. I mean, if you have a fast connection, definitely helps. Okay. All right. So yeah, you don't need a desktop. That's the whole idea. Okay, Chinmay, you don't have your hand raised either. So do you have an issue or didn't understand something? I mean, not just the setup, but anything we have taught so far, like what Santanu did about the modeling. So going forward with the lab, are you comfortable or are you just like going to like, okay, so you didn't want to answer, so you just raise your hand that you're okay with it. Okay. And then uh, Parmita Rath, you're okay so far? Okay. So about Ashwini Kumar, what's your issue? Ashwini, are you there? No, I'm John late, so I did not understand regarding the lab session. Okay, well, it's your job to catch up. Um, so this, I think, I'm hoping you're all good. Animesh, you're all good or you have issues? Are you there, Animesh, or somebody else is watching this? Okay, how about Soumya Ranjan? Soumya, you have any issues with the labs? Because you have,
No, no, sir.
okay. Priyanka, you're fine? You'll be okay with accessing this lab?
Yes, sir.
Okay. All right. So I guess you just, okay. Let me know if you have any issues. Like I said, the whole idea we did this is, um, so that you don't have to go through all these hoops. All you need is a browser and internet connection. I can't do better than that. Um, I mean, if you don't have a internet connection, then you have to download. I mean, you can't watch anything anyways. So that's like, yeah, but you do need a laptop. Without that, you can't do this on the phone. All right. So, and here, if you go into the GitHub page, you'll see I've added two links to Linux and Vim. People who are absolutely new or, they just did something a long time ago. These are two great tutorials. Each one should not take you more than half hour, 45 minutes. So the first one is just going through a lot of the commands, command line commands we use in Linux, like the ones I was using right now. And Vim is actually the editor which I just use. You can use another editor if you're comfortable with it, that's fine. But Vim is probably the most popular. That's the one I've been using for I don't know how many decades now. So um, and that's a very popular one, and it has style files for a lot of like you saw, right, when I opened the MD file, it automatically styled it, so you don't need ID or anything like that. Okay, so definitely go through these 2 tutorials. All the references are here. And then as I showed, once you have the terminal, once you start Su2, you have the documents there as well. I'll put the BSIM 3v3 and the other document there. And just follow this instruction, get it going. Okay. Any other questions? All right. Something, did you want to add anything or?
No, sir. Only thing I'm worried about that they have to use all this facility.
Yeah, well, you know, it's like Srikant was saying on the first day, right? We'll take the horse to the water hole. I mean, if you take his head and bury it inside the water hole, the horse will die, right? So we are taking it to the water hole. After that, you have to just put your head down and drink it. I mean, that's all you have to do. Um, yeah, I mean, like as I said, eh, you know, this is what I typically see. We'll give them all these opportunities and all that, right? In terrific course, because I've seen the industry. I know the quality of training which goes around, not just here, around the world.
Yes.
Um, so we give this, and then they go, don't learn anything, and then suddenly they're like, oh, I'm not getting a job because, well, I didn't learn it. And they'll go spend like 1 lakh, 2 lakh. There are these uh,
Mm,
school, like these training institutes like Moven and RV and all that. These places, honestly, I shouldn't speak while it's being recorded. Let me. Yeah, actually, I wanted to just quickly show to the people who missed about the lab, but looks like half of them, maybe those are the same guys again missing. Maybe in the end we'll show it to them. Okay. Um, all right. So, we'll, um, discuss maybe not just problems, but, some qualitative questions also about most of the MOS, mostly related to the MOS, device, the threshold and current and all that. So, okay. So first, let's start with the threshold. Um, so, everyone remembers the VT equation now. So it's the work function difference between the metal and the semiconductor. A lot of places it's called GC, and or the flat band voltage, right? And the depletion charge divided by Cox plus the Fermi potential, and then you have the adjustment you want to do for your threshold device. Then whatever impurities you have, all that adds to the VT, right? Okay, so first, by the way, so what are the um, things VT is, so from this equation, what are the things VT is dependent on? And from those, what does a designer have a control and what does a designer doesn't have a control? Okay, so maybe I can just give one example. So for example, Fermi potential, obviously it's dependent on the Fermi potential of the P plus, but does the designer have a control on this one? So same thing, what else is, what else does the VT dependent on, and if the designer has a control on it? Anyone? Just raise your hand if you know the answer, or just make an effort, right? You just have to discuss, right? You don't have to worry about if it is going to be wrong or right, or if you feel like, oh, I know this, I shouldn't say this. Just make an effort. That's the. Let me just first clear the hands first, because I don't know if it is from the last one or. So can we say that we can control the Fermi potential by doping? Okay, so and Chris Madhu says dielectric constant. So when I say designer, I say about the circuit designer, right? So a circuit designer is someone who's using a process, right? He's not a process guy. So for example, I have decided to use the TSMC 180 nanometer process. Once I decided to use that, I can't tell TSMC go and change this, go and change that in the process, right? TSMC allows me to, as a designer, to change something. Like for example, in a MOS transistor, it allows me to change W over L. For a resistor, it allows me to change the W over L. For a capacitor, it allows me to change the W over L, right? For metal, it allows me to change what width, what length I want within the limits, right? These are the things that designer is allowed to change size. So that's what I'm asking. In this VT equation, what is a designer? As a circuit designer, I don't have any access to the process fab. So as a circuit designer, what am I allowed to change here? So let me start with the
So,
first one. Yep.
so we can change the ion that is DA. We are giving that ion to make the negative threshold voltage to positive. So
Sandhya, you are, you're muffled. It seems like, the microphone just got muffled, so can't hear you properly. Can you talk closer or something?
sir,
Yeah, it's better now. Go ahead.
sir, we are giving the ion to make the negative threshold to positive. So we can control the DI value. Can we?
Right. But this is more like a kind of a professional question. Yes, you can control a DI, but as a circuit designer, you don't have control on that, right? Like the model file you got, that model file is from the foundry house, and the VT0 is given to you, right? VT0 is given to you, so
Yes.
you can't control that. So yeah, these are all what decides the VT, right? But my question is, as a circuit designer, what can I control? So Somya
Sir,
says doping, but again, doping, I don't have any control.
so
Body effect, yeah.
only, sir, only the length and the area of, we can control. If,
Okay,
so
but so the length and the area of the MOS, right? That's the gate area you're talking about, I guess.
yes, sir.
Um, but where is W and sorry, this is L. Let's say this was your source and drain, L, and this is your, where is W and L in this picture? So I should be precise. So VT0 for VSB equals to 0 volt.
Sir, I am trying to say that saying that we can only change the COX value. Means with changing the
Now, again, COX is also fixed. You remember T ox is, let's say, for um, like for 0.18, I think it's about 2.7 nanometer. I think that's what we calculated yesterday or some. But this is fixed by the process. Once you decide you want to use a 0.18, as a designer, you can't do anything about it. Okay. So these are all process parameters, right? QB, which is dependent on the doping, that's a process parameter. Fermi potential, which is dependent on doping, that's a process parameter. The work function difference, the contact potential, it is again dependent on the material and the doping. That's decided by the process. The impurity is already decided. This is also already decided. COX is already decided. So actually, I don't have any control as a designer. um, I don't have any control. Okay, so um, so I think a lot of people are saying I can change the oxide thickness and all that. No, you can't change those. As a designer, you can't change it. That is something which is given to you. Once you choose a process, you say, I want to go with 180 nanometer TSMC process. These are what's given to you. Now, there are different flavors of devices. So they'll give you a high VT, they'll give you a low VT, they'll give you a IO device and all that. But for those given devices, it's fixed. I can't do anything about it. Okay. Um, is that clear to everyone?
No, sir, you can't even change the normal thickness of the material, right?
No, you can't, right? Like I said yesterday, right? Not yesterday, but day before. As a designer, you have control on X and Y. Okay. The Z direction is all process. Okay. Anything which goes in the Z direction, I have no control on it. So when it comes to geometry, I only have control on XI, widths and lengths. That's it. Height, I have no control on. So all these um, heights here, the depth of the N plus, P plus, and so on, these I have no control. That's already decided by the process. If you are a processing guy and you're designing a process, then you have access to all this, right? If you are a process engineer in TSMC, or you're a process engineer in or in India like SCL, which is the only fab we have, or you're in Intel, or you are a process engineer in um, global foundries, then you say, oh, I want to do this device which is really fast, has low VT, low leakage, and all that. And then you say, okay, I don't want to heavily dope this. I want to do salicide here. I want to do this. So then the whole world is your um, canvas to do that. I mean, obviously limited by the physics, but you don't have any control on the vertical direction. So sir, we can control the charge by putting different potential. Yeah, but I'm asking, of course you can do that. So you can put a voltage here, change the voltage, and the charge will be different here. But the charge, the VT, there is no dependence of WL and charge voltage to VT, right? VT is these parameters here. And if I take the complete equation, then it is, sorry, VT, let's say VTN, then it is VT0 plus, gamma times root of 2 phi f plus VSB minus that, right? Okay, now with this equation, now tell me what can you control as a designer? Yeah, VSB, exactly. So that's the only thing you have under control as a designer, is you can change the source voltage. And obviously in digital design, you never do this because very rarely you do that. But in analog design, actually people do that. They control the threshold. So low voltage, a lot of low voltage designs, the input is actually given to the source and bulk instead of gate to source. So gate, a lot of low voltage, not a lot, but there is a there's a fringe community which uses that, and so you can. So yeah, in this equation, as a designer, the only control you have is on VSP if you want to change VT. And what I haven't shown you here is VT is also dependent on temperature. Okay, it is actually inversely proportional temperature. The hotter it is, the lower the VT is. Colder it is, the higher. Okay, so there is a temperature dependence, and that temperature dependence mostly comes from the dopings. Okay, so the doping, your carrier, free carrier changes, and because of that, your VT changes. Your COX doesn't change a whole lot. I mean, it's very slightly, but mostly the doping actually changes. And because of that, I mean, your free carriers, and because of that, your work function also changes, is also a function of temperature as well. So there's a dependence on temperature and all these process parameters. So obviously, this temperature is a, this is fixed, right? Once it gets out of the fab, this is fixed. So the only thing you are changing as a designer is the source bulk voltage. And the other thing which changes, and this is not something which the designer wants, but it gets, like the temperature variability, right? Because you want the VT to be constant most of the time in your design, to be constant over the temperature, but that's just what you get. And then you have to compensate it by designing, either over designing or doing temperature compensation or whatever it is, right? So we haven't discussed the temperature dependence, but it is very strongly dependent on temperature. So for example, from going from -40 to 125, which is the industrial range. So let's say you're designing for automotive or industrial application, then you have to meet all the specs from -40 degrees C to 125. And a typical VT will vary. Like for example, if you have zero point 0.4 volts or zero point 0.6 volts nominally at 27 degrees centigrade, from -40 to 120, it can vary all the way from 0.4 all the way to like 0.8. So depending on the process. Okay. Is this clear? So I think a lot of people, I think Somi also got that in the beginning, that you can control it. So the only control, like I said, is VT. So VT is really a process parameter given to you, okay, as a designer. So that's one thing you got to, looks like a lot of you had that, didn't have that clarity. As a circuit designer, you can't touch any of these. Okay, they're all fixed. Okay. Makes sense? Any questions? All right. And in a Nmos, typically the gate is always N plus poly, and in a Pmos, the gate is usually P plus poly. Why is that? There should be an easy answer for you guys now. Quick.
Sir, can you repeat?
So in a Nmos, let me just so I'm drawing a cross section now. In a Nmos, so this Nmos, this is P minus, this is your oxide, this is your gate, right, which is poly. This is a N-doped poly. Okay, poly. In a PMOS, this is a P plus poly. Why is that? And can I change it? If I change it, what happens? Soumya, you're saying power conservation. I didn't understand. What's the power conservation about?
So I mean, if we change the gate, so without giving any voltage, it will form a channel.
Okay, we'll come to that. That not necessarily, but it's actually the opposite. But yeah, we'll come to that. But my first question is, why is it the case? Why is in
Sir,
NMOS the, yeah?
we won't get a fine line in the well.
What do you mean by that?
Like when we diffuse the N plus in the well, the like the fine line which we get, that is not exactly that fine, right? So If we change that, we
Okay,
are
I
not
think
able to.
you are getting there, but what is the term called? Like we have been talking about the term. Like how do you form the diffusion um, for the Nmos and Pmos? How do you create the source and drain? You remember the processing step? How do you create it? Come on, guys. We have been like saying this on and on and on again for during the processing. What is the steps in creating? Okay, tell me the steps now. We did so many problems. What is the steps in creating a Nmos now? So I have a bare substrate, okay, and I did a layout. Let me erase this and do a layout. So I do a layout where I draw the diffusion and then I draw the gate here, right? Forget the metallization and all that. Let's just do this. Yes, correct. I think few of you are getting it now. Um, Sandhya says self-alignment, bombardment of ions. Jackie says self-alignment. Soumya says ion bombardment. Well, it's not just because of the ion bombardment. So this, you're saying P plus poly, it creates a N channel due to induction. I didn't follow. What do you mean by that? So this, can you explain what you meant by that?
Sir, actually, you are asking that can we change like people for Pmos, can you change in like we can you change that
Well,
N mode?
my first question was that why is it P plus, always P plus? Like, in a CMOS process, the gate is N plus poly for Nmos and P plus poly for Pmos. So that was my first question. And I said, after you answer that, I wanted to ask you, if I change it, what will happen? Let's say I
Sir,
can take care of cell. No,
if
first
you change
answer
it,
me, why is it P plus N? You didn't answer me that. So are you convinced that it is self-aligned because of self-alignment?
uh, self-alignment, I am not I'm not denying that because I'm not sure whether
No,
that
no,
is the reason or
no.
not.
Yeah, but you seem you're not convinced of that. Why not?
Uh, the self-alignment maybe that is basically depending on that masking, I guess,
No,
because
no.
of
So
that
tell
mask.
me now. Let's go through this process. I have a wafer, and I have
Yes,
two
sir.
masks, right? I have the diffusion and I have the gate mask. So tell me the process of like using this two masks to produce the transistor. What is the process steps? What is the first thing I have to do?
So the red one is the piece of tape.
Diffusion. Red one is diffusion. So source drain, basically diffusion. And this is poly. Green is poly. So what is the step?
So first we have to go for SiO2 SiO2 layer, then we have to go for metallization over that.
There is no
Then
metal here. There is no metal here. Just gate and source and drain. So first you did all the processing step and did what? You did the thin oxide. First you put the thin oxide, use the polymask and remove the thin oxide, and then you put the poly. Actually, you put the thin oxide and poly together, and then use the mask to remove it, right?
yes, sir.
But this poly is an undoped polycrystalline. There is no doping, right? And then what do? You take this mask and then you do the diffusion or ion bombardment and alignment and create the N plus, right?
Yes, sir.
And the self alignment is because this mask is there. I mean, this poly is there. It stops the N plus, but in the process, this gets doped N plus. And that's what you want to do.
Silicide and polycide something.
Yeah, the silicide is after. This is just purely bombarding. Silicide is nothing to do with the poly n plus poly. Silicide is another layer on top of p poly. Okay, so that is another very thin, kind of a highly conductive tungsten. I mean, not tungsten, titanium, or whatever silicide layer they use, and it's also on this as well. Okay. So it's because of self-alignment, right? Because you are using poly as the mask to avoid n plus being diffused into the channel area, but it itself gets bombarded with that, and that's why you get n plus and p plus. So is everyone convinced about that? Yes or no? Let me know. Okay. Just okay. Good. At least the usual suspects are convinced. All right, so now I ask the follow-up question, which I just asked before. So what I'm asking now is this. You have, so you have the substrate, right? And for a Nmos, so we had N plus, we use the thin oxide, the gate. Now what I'm saying is that this is a hypothetical case, right? I mean, I can do it. Maybe there is some alignment. Instead of a N plus dope, I do a P plus dope. Okay, P plus dope poly. What happens to my VT compared to the last one? So let's say last one, I'm going to call it as VT standard. So VT standard Nmos. Okay. Now, when I do this, I'm going to get a VT. Is this, so I'm going to call it VT new now. Is VT new going to be greater than VT standard, or less than, or equal to, or this transistor is just dysfunctional, it will not work? What do you think? So maybe I'll write the VT equation here again. And this is obviously assuming source bulk is 0. So we'll just talk about VT 0. So phi gate to channel plus 2VF plus QB. And I'll just neglect the rest of the term for now. I at least have the implant, I guess. Okay, so just looking at this, what do you think will happen to the VT? So this is saying channel width will be decreased. No. See, my problem statement is I'm saying that you're trying to say that physically something will change because I'm not doing self-alignment now. But don't worry about that. I'm saying I've figured out a way that I'll align it properly and all that, but somehow I'll manage to dope it with P plus. So it's a bit of a hypothetical question, and people do engineer that. So then what will happen to the VT? So, okay, Sandhya Rani says in both Somya, this is less. Okay, Sandhya, why? Give me a reason. Why do you think it'll become less?
Sir, we take less voltage to form the channel here when we consider P plus at the, because all the electrons are attracted to form the channel, so we require less threshold voltage to
Yeah,
make it.
but why? I mean, what in this? So, before whatever we had. So basically, if you're saying it is less, then one of this or all of these quantities are reducing by having this VF. So which one do you think is reducing, or all of them, or some of them? So let's say I don't change the implant, right? So this is fixed, correct?
Yes, sir.
So this is a fixed implant. So this doesn't change, Sandhya. How about this one? If you remember when we did the derivation to find out the dV, this is dependent on the doping of P minus here, right? That's what is deciding. So this actually, how about this one? This one actually change is dependent on the doping of the P minus as well, right?
Yes, sir.
So I think Sandhya is having some voice problem. Can you tell me?
So can I audible now?
Yeah, you're audible now. We can hardly
Yes,
hear you.
sir. Both are dependent upon the ion P plus ion. The
Which
QB,
ones? Which one is dependent on P plus?
the form the 25F and QB by COX,
No, that
because
is that. Yeah, that is dependent on this one, not this one. Okay, so yeah, so maybe that was a confusion some of you have. So when we calculate QB and we take the acceptor ion, this thing, because you remember this was N plus, right? And we always took the acceptor ion to calculate these two. So that's dependent on the substrate because you're talking about the surface potential of the P and the QB of the P minus. That we are not touching, right? You got it right. So actually none of these should change. What about this one, 5GC? So what is this contact potential? It is the um, so if you remember when we drew it, this is your vacuum level, right? And then your n plus. So I'm drawing this direction now in this direction here. So I'm going top to bottom, but drawing left to right, right? So you have your oxide here. This is, let's say, your oxide, and this was your initially this was your n plus, right? So n plus means, let's say this was your conduction band, and so n plus is very close to here, and that's your valence band. And for the p side, the p side was, this was your conduction band, valence band, and your p side was here, right? So this was phi p poly, let's say, minus phi semiconductor, right? So and phi poly was, actually let me just erase this 1 second. Let me draw it here. Let's say this is your uh, um, so the energy which is required to take the electron from this Fermi level to vacuum, that's called the work function of, in this case, it will be Pauli. So let me call this N plus, right? And then the energy which it requires to take from the P substrate to vacuum is this, and this is the phi P plus, let's say, right? Or P minus, or the substrate. Let's call this phi S substrate. And let's call this phi poly, right? So you can see that I'm doing this minus this. That's why we got a negative number, right? We got like 0.25 or something like that, if you remember, which is this difference here, right? But if I make this as P plus, then this ferment level will drop. It'll go here, which means that this difference will drop, which means that this negative term will go up in value. Okay. And because of that, the VT0 will actually increase. So I think somebody mentioned that, oh, we'll actually have a channel. No, you actually have a channel because you have an N plus. If you actually have a P plus channel, most probably you may not need the QDUI COX, but you get the N plus channel because because of the self alignment, and that's why you have to do the adjustment. Are you guys convinced, or didn't make sense? Or so basically, the key thing is that these are good, even though they're hypothetical problems. It's good to go through them because I think some of you are thinking the acceptor ions for QB, FEF were from the gate. It's not, right? It's from the substrate. So the only thing in that equation, ideally, which is changing it is the contact potential, right? The difference between the Fermi potential. Yeah, I think so. Ashwini and Swadesh, they were saying that the Fermi potential will decrease. Yes, correct. Which means that the work function will increase, which means the difference between the work function will actually decrease, but it's a negative number, so your VT will actually increase, right? Will become more positive. So yeah, so if you want to be accurate, because it's a negative number, you shouldn't say decrease, it should be increasing, the work function difference. Is that clear, or you guys have any questions or doubts regarding it, or not convinced?
Sir,
Yeah.
sir, on which components phi f depends?
What is the expression for phi? It's the thermal voltage log of the doping concentration over the intrinsic, right?
Yes, sir. Ni divided by Na.
Right. So it's just purely dependent on the doping of that material, right? So if it is a N plus type, then Pf is negative. If it is P plus type, then it is positive.
So
That is the
changing
Fermi
that,
potential, but the work function is just with reference to the infinity. So you're just taking the work function difference. And in case of B plus, that difference is decreasing, right? And because you had a negative number, if that negative number is decreasing, which means that the VT 0, which is a positive number, is increasing, right?
yeah,
So, in that example we had taken, we had Fermi potential. Okay, look at it this way. What if yeah, maybe this is a good way to explain it to you guys. You remember, um, I said yesterday, the contact potential, doesn't matter what you take the stack, right? If you have some material M1 here and some material MX here, okay, then the contact potential, which is this phi GC term here, this phi M1X is equal to phi M1X. It's the two end ones, right? So what if I made this gate um, um, doping exactly the same as the substrate doping? Then it'll be 0, right? So if you remember yesterday when we did the VT calculation, we had whatever minus, um, I think it was like, so we got minus 0.6, so it was like most like minus 0.6 or something, the potential difference, and the QB was immaterial, and then we had 2 phi f as 0.45 or something like that, and the VT came out to be minus point, in this case showing 0.15, but so let's do this 0.65. So something like minus 0.2, right? This is the number we got. And then we added a plus term here by doing that ion bombardation, right? Now, if the gate doping was exactly same as the substrate doping, then this term will become 0, right? Because it's phi x minus phi x basically. And then you'll get a positive 0.45 volts, right? And essentially you're going in that direction, right? You're going from N plus to basically P plus. So it's moving in that direction. Ashwin, please explain the diagram once again. Explain what? Like what is, I mean, I explained this diagram a couple of times. What is it that you want exactly? Ask me something specific. So Ashwini, what are you trying to ask from this? Which diagram, by the way? The band diagram or this diagram or this diagram? Which diagram are you
It's a Venn
asking?
diagram.
Okay, what is it you want to know? Your
So
questions
how
are
the
always
PF
like
is,
explain the chapter or something like that.
no, sir, how the PF is decreasing?
The PF is not. Why is this decreasing? This one?
Yes, sir.
Well, that's if you dope it with a P plus, then you remember the band diagram, right? Sorry. This is the conduction band, this is the valence band, this is your intrinsic Fermi level. If I dope it as a N plus, where is going to be my Fermi level? Close to the conduction band or valence band?
Conduction band,
Okay, so that's his N plus. How about P plus?
valence band.
That's what is happening here. So what are you confused about?
So why we can't take P as the gate? That I cannot understand.
No. What is your question again?
Why we can't take P as the gate in Nmos? P plus
No,
as the
it's
gate in.
not. We cannot take P as gate. We want to have as a P plus as a gate. It's not like you cannot have it. It's just that the process where you do self-alignment doesn't allow you to do that, right? Because you do the ion bombardment after you put the polycrystalline. So if you're doing it for Nmos, you're bombarding with N plus. That's why you get N plus, right? If you do a P plus after that, then your source and drain also will get bombarded with P plus. You don't want that, right? Is that clear or?
Okay, so will this work? This type of gate?
You mean if it was a P plus?
Yes.
Yes, it will definitely work. Why not? Because it has mobile charges, so it'll be able to take positive or the negative ions, right? So it'll definitely work, right? In fact, ideally that's what you would want for NMOS. Then you'll get an enhancement device by default. You don't have to do any adjustment. But as a process, it's if you do that, then you can't do self-alignment. If you don't do self-alignment, then it's extremely difficult to do fine line transistors.
Okay, sir. Thank you.
All right. How about rest of you guys? Are you convinced or have to figure it out? So if you won't put the SiO2 layer but poly and metal, what will happen to the CMOS? You mean the thin oxides for this? I don't understand the question. So you're saying poly but poly and metal. I still don't get it. So what's your structure? You have what is your structure? You have this N plus P plus. So you don't want oxide here. So you want just poly here? Is that what you're talking about? Okay, but if you have a poly here, this is a P to P contact or N plus to P contact. Now you have a diode, right? So you have a N plus to P minus contact. So the source and drains are, uh, so it's like almost like you have a parasitic BJT basically. Well, first of all, if you do N plus here and you have this, you almost all the time you're shorted here, but essentially it's just a diode, right? It's N plus P minus diode. Okay, any other questions? Okay, I should take some let me do some region of operation. So let's say if I have a NMOS and I bias this at 1.2 volts, 0.2 volts, and ground. This is Nmos. Ignore body effect. So I imagine gamma is equal to 0. What region of operation is it this in? Cutoff, linear, saturation. What? Oh, sorry, VT. I have to give you the VT value. So VT is 0.4 volts. Okay, Praveen says saturation. Soumya says saturation. Saturation. Who else? Come on, guys, fast. So this one you should do it quickly, like at least. Okay, so the saturation. Okay, Praveen, maybe you can come in line. So how is it saturation? Can you explain, Praveen? VGS minus VDS is less than VT. Okay, so why is it saturation? I mean, what are the conditions for saturation, Praveen?
Hello, sir. Am I audible?
Yes, you're audible. Go ahead. So what is the condition for saturation?
It has to be in saturation that at the drying end it should get a tapered waveform. So at the drying end it should come towards source and it will not be a gradual channel approximation anymore.
That's correct. Not a waveform, but channel. Yeah, the channel charge pinches off there. But what is the voltage conditions for the 3 terminals for that to happen? What are your conditions?
The condition which I wrote there, like
That is the only condition you have? Okay. All right. So let me maybe ask Soumya. Soumya, what's sorry, 1 second. Or Swadesh. Swadesh, why are you saying it's saturation? Okay, Srishti says VGS is greater than VGS minus VT. VGS is less than VDS. Okay, so looks like you guys are, I thought you'll absorb it pretty. So, okay, can somebody tell me what are the 2 conditions you need for it to be in saturation? So you guys are all giving me 1 condition, but you need 2. What are the 2 conditions?
Both the VDS and VGS should be less than gate voltage.
Both VDS and what else?
And the source voltage and the drain voltage should be less than the gate voltage.
Okay, but the source voltage is 0, so which means that you want VD should be less than VG.
Yes.
Okay. Although I said I don't want to review because that will be too boring, but none of you guys, you guys got to just at least review it, right? VGS less than, greater than VT 0. You remember when we reviewed it, there are 2 conditions which are needed for you to find out, right? What is the first thing you need to check? What is the first thing we did before we did the IV characteristics? What is the first thing we derived in the Mos? Yeah, I think Soumya, you got it right, but everyone else is seems like they're just throwing numbers, VD, VGS, VD less than that and all that, right? What is the first thing you have to determine before you do? What is the first thing we did derive? What is the threshold voltage, right? But the threshold voltage, okay,
Yes, sir.
right.
Here one more thing, sir, like here VGS is not VGS is less than VT. So
Yeah, that's the first thing you want to check, right?
yes,
Correct,
yes,
Praveen.
sir. Yes,
You will first want to check if there is a channel. If there
yes,
is
sir.
no channel, if your VGS is greater, less, equal, doesn't matter. You don't have a channel. What are you
Yes,
going to
sir.
conduct, right? So the first thing you have to check is VGS greater than VT. Now, I think some of you are confused about which is VGS. I think some of you are thinking this is VGS. This is NMOS, right? This is higher voltage than this. That means this is drain, this is source, this is gate. This is VGS, right? And VGS is equal to zero point 0.4, I mean zero point 0.2, and VT is equal to 0.4. So clearly there is no channel. So it doesn't matter what the VDS is. So this is cut off, right? So I think Somya is the only one who got that. Um, so first thing you have to, in these problems, you have to first find out if there is a channel formed or not. And for that, you have to figure out if VGS is greater than VT or not, right? Then you figure out if you can do it or not. Okay, let me change the problem a little bit now. So I'll say still NMOS 1.2, 1.2, and let's say this is 1.1 volt. What region of operation? And everyone else, there's only like 2-3 people responding it. I mean, there's how many people online? 40, well, like 35 plus people online. What about the rest? You guys are completely clueless. If that's the case, why are you not asking question? If you guys are all raising your hand that you understood it. Give me a second, guys. Just think about it. Okay, sorry, I'm back. Yeah, correct. It is. So I think now you guys are getting cut off because this is the NMOS, right? So this is at a higher voltage than this. So this is drain, this is source, this is gate. VGS is VG minus V source, which is equal to 0.1 volts, which is obviously less than VT, right? It's in cutoff. Everyone agrees with this? So you don't need to find out what VDS is. If it is in cutoff, that's it. You don't have to know what VDS is now because the transistor is, off. It's only when it is on, then you figure out if it is in saturation or in linear region. Okay, now let's take another problem. So let's say this is, let's keep this ground. What is the region of operation for this one? Okay, province is linear. What about the rest? Quickly, guys, like I said, there are 40, 35 plus people. Why are only 2-3 people answering? Okay, linear. Yeah, so this is drain again, this is source, this is VG. So VGS is greater than VT, right? Because 0.6 is greater than 0.4, and VGS minus VT is what? 0.2, which is greater than VDS, which is 0.1. I mean, sorry, yeah, greater than 0.1, which means VDS is less than VGS minus VT. So this is linear, right? Okay. Okay, let me do a Pmos now. So if I have a Pmos, and we'll do 1.2 volts and 1.1 volt, and this is 0.9 volts, 0.9 volt. Okay, and VTP, which is a negative number, so I'll make it minus 0.4 volts. Okay, what's the region of operation? Okay, so Mrs. is cut off. What about rest? Province is cut off. Come on, rest. At least I want like 10 people answering out of 30. Everyone can't be sleeping. Even if you're like doing a coin toss and picking one number, like one region of operation, that's fine. Just write something. But then I might pick you to answer. Give me an answer. Okay, cut off. So, okay, Sumant, maybe you can come online and explain. So why is it in cutoff?
Because the VGS is greater than the VT voltage.
Well, if VGS is greater than VT, why is it in cutoff?
So that's a condition.
For Pmos. No, but this condition, you're taking this condition? Sumant,
Sir?
did you say this is in cutoff because VGS is greater than VT?
Yes.
But we said VGS greater than VT is channel on here. Sumant, why are you unmuting yourself? I'm asking you a question.
Uh, Actually, I did that with that condition. So now I'm just thinking.
Okay, which is the source and drain here in this
Sir,
Pmos?
the left one is grade, down one is drain, up one is sorry, down one is source, up one is drain.
This is source, this is drain.
Yes.
Okay. All right. You guys need to review a lot. Let me ask someone else. Srishti, so can you come online? Srishti, are you there? You said cut off. I just want to find out why you think it's cut off. Okay, how about Devanand? Hello, Devanand, are you there? I don't know what's going on. Why why aren't people able to answer? Are you not able to mute yourself or? Okay, Priyanka, why is it in linear? Why can't you unmute yourself, Dhwana?
Sir, in Pmos, if BDS is less than VGS minus mod of BT, then it's linear.
Sorry, say that again.
In Pmos, if
Yeah.
VDS is less than
VGS.
BDS is less than VGS minus mod of BT.
VGS mod of VT. This.
This is linear condition.
But you remember we said, right, first you have to find out if the channel is on or not.
Yes, sir.
So what is the condition there?
The condition is BT should be greater than VGS.
VT should be greater than VGS.
Yes, sir.
Or VGS is less than VT.
Yes, sir.
Why is in the Nmos it's the opposite?
Because BT in Pmos it's negative.
Correct. And so what is the drain source in this terminal here? What is the top node? Is it drain or source?
Sir, it's opposite. Drain should be in drain should be extent.
So this is drain, that's source, right?
Yes, sir.
This is gate. Okay. And so VGS would be equal to VG minus VS, which is equal to 1.1 minus 1.2, which is equal to minus 0.1, right? And VTP, I said, is equal to minus 0.4 volt. And you're right, the condition is VGS should be less than VT because it's a negative number, but VGS is actually greater than VT because minus 0.1 is greater than minus 0.4. Okay.
Yes, sir.
Okay, good. So, so you guys need to review the at least the conditions a lot, like because you know there's a lot of confusion it seems. So the first thing you have to do, and PMOS is always confusing when you start. So the first thing you have to do is you have to figure out which is the source and drain, right? So you remember the higher potential is because you're putting a battery, right, which is positive carrier. Uh, the reference is positive carrier. So the source end is the one which is the source for this. Because this is P plus and your current is flowing, positive carriers are flowing in this direction, then this is the source of your majority carriers. That's why this is source and this is drain. In the Nmos, that's why it's the opposite. And this is the gate, right? So in Pmos, whatever this voltage is, right? So let's say this was 1.8 volt and your VTP was equal to minus 0.4 volt. That means this gate has to be lower by 0.4 from this voltage here for this channel to turn on, right? It's the opposite of NMOS. So if this is 1.8 volts, channel is not turned on. If it is 1.7, channel is still not turned on. 1.6, barely, I mean 1.6 still not on. 1.5, it's still not on. When you get to 1.4, this difference is now VGS is equal to minus 0.4. And after that, it becomes minus 0.5, so on, and the channel turns on, right? So this is obviously in cutoff, right? Okay, let me change this now. So this is 1.8 volts and VTP is equal to minus 0.4. And this is, let's say, is 0.6 and this is ground. What is the region of operation? Just give me a second, guys, 1 second. Yeah, think about it and Okay. So what is the region of operation for this, the one I've shown? Range says saturation. Soumya says cutoff. Okay, more people, please. Cutoff, cutoff, cutoff. I think people are just throwing terms right now. Okay, Krishna, can you tell me why it is in cutoff?
Hello, am I
Yes.
audible?
Yes,
Hello.
yes, you're audible. Go ahead.
So here the VGS is minus 0.6 minus 0.6 minus 0, and the final term will be VGS is equal to minus 0.6, and minus 0.6 is less than the VTP, which is minus 0.4. That's why it is in cutoff region.
Okay. Don't mute yourself yet. So you said this is gate, this is source.
Yeah.
We just said, right? This in PMOS, the positive side is the source, and this is the drain.
No, the upper side is source and the lower side is drain. Right.
Okay, all right. So say, but then how come it is? What did you say?
Mm,
0.6 minus
I-
0.6.
Yes, sir. I will rectify it, sir. I mistaken by mistakenly I have done that.
Okay,
Sir,
all right,
now for that VG is equal to 1.8 0.6 minus 1.8.
correct.
Yeah,
And so what is it now?
and that will be
Right?
yes, sir. Yes, sir. So
Okay, and
1.8.
VT is minus zero point
Minus
0.4. So
yes,
okay,
sir.
so what is the channel on or not?
Sir, now the channel is on, sir.
Okay, good. So it is not in cutoff, right? So channel is on. So
Yes,
now
sir.
what is the
Yes,
second
sir.
condition you want to look for? Now it is a PMOS, so VDS should be what?
It's a linear. Sir, it will be in linear condition.
Why is it linear? What is the condition for VDS?
Sir, for linear, sir, VG is greater than VT. So no, it's cut off because sir, VGS is equal to minus 1.2 and VT is equal to minus 0.4. So minus 0.4 is bigger than minus 1.2 in minus step. That's why it's in cutoff reason. Sorry.
No, but okay. You remember, right? In PMOS, if you keep the sign, then it is VGS less than VT, then channel is on, right?
Yes.
If you don't keep the sign, then you can do this, right? Then it is channel on. So you said it correct initially. Why why are you why
Yes,
are you
sir.
retracting back? So Priyanka says she's totally confused. Good. Confusion is good. Then you start working on the problem, you'll let know.
No, sir. I know that, sir. I'm nervous, sir.
No,
Sorry,
I
sir.
think Priyanka, so I just saw a text saying that she's totally confused, which is good. Um, I mean, it is confusing in the beginning. So that's why I said you figure out a system. If both is working out for you, then it's fine, but figure out a system and then stick to it. Okay. So let's quickly review this. Okay. Okay, let's do Nmos first. In Nmos, this is gate and drain is always higher potential than source, right? And first you want to check if VGS is greater than VT. If so, then you check if VDS is greater than VGS minus VT. That's your condition for, uh, let's do the linear one first. If it is less than VGS minus VT, then this is linear, right? And for NMOS, it is pretty straightforward. So everything is positive. So let's say this was ground, this is VGS, this is VDS. So everything makes sense, right? then for saturation, VDS is greater than VGS minus VT. And look, go through the derivation. We went through in such detail. Why is that the case? Why is it pinching off, right? We went through the channel, looking at the channel charges as we were going through. Pmos, you just have to work it on yourself and check that it is the opposite, right? So these are essentially your three conditions you want to look at. Basically, you have to first start to see if VGS is greater than VT, and then check if it is linear on saturation. If VGS is greater than VT, then it is not cut off, right? Otherwise, it is cut off. Then you don't have to check any of these. For PMOS, the higher potential node is the source, and this is the drain. This is the gate. That means VGS is always negative, right? And VTP is also a negative number. So which means that in order to turn this channel, I want to be lower than the supply or the source side by a certain amount, which is your VTP number, right? So for example, if VTP is, like I said, it's minus minus 0.4 volts, then and if this is 1.8 volts, then I want the gate to be 0.4 lower, at least 0.4 lower than 1.8 before the channel turns on, right? So as long as the gate voltage is from 1.8 to 1.4 volt, it is in cutoff. And once it goes lower than that, that's when it'll go and do it. And you can swap terminals if that is, instead of doing mod. So instead of doing VGS, you can do VSG and VSD. Sorry, VTP is still negative, so you can do VTP positive and VSD and convert them all into positive numbers as well. Okay, but let's stick to just the original one, right? So if this is the case, then VGS, you have to check if VGS is less than VT first. That's your first condition. And if that's true, then you check if VDS is greater than, because VDS is also negative, right? So if it is greater than VGS minus VT, which is also negative, then it is in linear. Or if VDS is less than VGS minus VT, then it is in saturation. And try to physically look at it, right? You see this PMOS here, right? You're applying this voltage. Remember, this is source, this is drain, which means that in order for this channel to pinch off, this voltage needs to keep going up and up and up, which means that VDS, which is the opposite side, should go more and more negative. Same thing, this gate voltage is lower than the source voltage, which means that to turn it on, this gate voltage needs to get lower and lower, which means VGS needs to get more negative, right? More and more negative for the channel to turn on. So you want this to be more negative, this to be VGS to be negative to turn it on. You want VDS to be negative to pinch it off to get it into saturation. And if it is all confusing you, like I said, take VSD and VSG instead of VDS and VGS, because this is really your reference node right now, right? So if you take VSG, this is your reference node, but it's a higher node. That's why everything is turning to be negative. So you take VSG, then everything will turn positive again. You have to take mod of VTP or take all mods, VGS mod, VDS mod, VTP mod, and follow this three. That'll work also. But find one, stick to it, and just use that. Okay. So what I'll suggest now, I want to do a couple of more, but maybe what you guys should do is go back, review the condition of operations and find out why it is so. Okay. And do the problems which Santanu is going to um, post it hopefully by tonight, and you'll get enough time, do all the problems, you do all the problems.
Sir, it's live
Yeah,
already. So
okay, it's live. Okay, great. So it's already live. You got so what did we give them till Monday night or something?
Monday 11:15 p.m.
Okay, so you got till Monday midnight. Go and do those problems. A lot of these problems are based on this, and some of them actually is what I was just discussing. Do that. I think it will become more clear, and then we can discuss maybe. Okay, maybe after you finish the problems on Monday, then we can do some question answers regarding this. Okay. So just make this clear. The condition of operation. This you just have to have this in your tip of your tongue. I mean, once you start doing CMOS, you can't be saying that it's linear because VDS is greater than VGS minus VT. I mean, if you get into any interviews, they'll just cut you off right away. So that is something you just have to get it right. And yes, especially the Pmos is confusing in the beginning, but the only way out, like I keep saying, is you just have to practice more problems. So Santanu has put a bunch of problems. Go and do those. I have put reading assignments and problems, extra problems on the GitHub page. Do those. If you and they're not, and I'm giving you like very targeted sections. Like I'm giving you 1 or 2 sections to just read. It's not like you're lost. Should I read this? Should I read the whole chapter? So, I mean, we're almost spoon feeding you right now. And so you have to get these things right. Otherwise, um, it'll be very difficult for you to do any CMOS design. Okay. So I have to go now. We'll stop here and we'll meet tomorrow 10 a.m. And like I said, you are all going to get an email regarding the lab login. I showed you the process. So Santanu, once you put that YouTube, just let me know. I'll put that link on GitHub page as well. There is a set of instruction there as well. Log in, reset your password, do the GitHub clone, shlone, and all that, and have it ready. And so tomorrow morning when we start, we should be all set to go. Okay.
Okay, sir. I'll post it now.
Yeah. Okay. All right. Thank you. Thank you all.